Hello and welcome back to my YouTube channel. My name is Professor Govalla, and today I'm going to be talking to you about the source-free RL circuit. And essentially what we're going to talk about is going from this circuit here, call it 1, to this circuit here, call it 2, where in circuit 1 we have a DC current source, or IO, right? And it's connected to my inductor via this switch at a t is equals to 0 minus, essentially meaning that my inductor has been charged up for a long period of time. And then at a t is equals to 0 and a t is equals to 0 plus, I move my switch to terminal 2. And essentially this circuit here is the source-free resistor inductor circuit. And the goal of this video is essentially trying to find out the natural response of this inductor as I move my switch from location terminal 1 to location terminal 2. And before we dive in, I always like to give a formal definition of the topic that we're talking about. And the formal definition is a source-free RL circuit occurs when its DC source is suddenly disconnected and the energy that was stored in that inductor, again, remember this occurs because when we have current through an inductor, a magnetic field is generated, and that magnetic field or that energy in that inductor is then released and dissipated to a resistor or a load connected to the inductor. So on a high level, why is this important? Why do we need to understand the source-free RL circuit? And we use it for something, for a couple of things, right? And one of them is signal timing, right? And this, for example, like a relay, right? And a relay is essentially a circuit that moves a switch electronically. Okay. Again, I don't want to dive too much into them, but signal timing is one of the things that you would use a source-free RL circuit for. Another topic you can use the source-free RL circuit is for current filtering, right? And if you wanted a low-pass filter for my current, I could use a RL circuit. And then you can also use inductors for transformers, right? And this is the transfer of electrical power. And again, in order to get to the level of using an inductor for things like signal timing, current filtering, and transformers, we need to first start off by understanding the low-level baseline, such as the source-free RL circuit. So now, in order to better understand what this circuit is doing, we need to take two cases. The first case being when t is equals to 0 minus, and the second case being when t is greater than or equals to 0. So in the first case, what we want to do is we want to imagine the following, right? Where my circuit has been charged up for a very long time. Okay. And what actually happens in an inductor is there is a thin film of insulated copper. So if you can imagine, there's a thin film of insulated copper here. So the current going through this inductor, called IL, has to follow this type of loop. So it has to follow this loop. All right. But after a long amount of time, what's going to happen is there's going to be no resistance to the current, right? So essentially, this is just going to be a short circuit. Okay. Again, let me go ahead and just put my RO here. This is my IO, or the DC source. So if we can imagine, IO goes into this node here and splits, right, into this IR. Okay, this is R. And what we consider this IS. Okay. And what's going to happen is when this IS goes through my inductor, it creates a magnetic field, right? Please check out my what is an inductor video. I've posted it in the top right hand corner of this video to understand why when current goes through an inductor, a magnetic field is generated. So essentially what happens now is that there's going to be no resistance. Okay. So essentially R is going to be equals to 0. That's the functionalities of an inductor. And as a result, IL of 0 minus is going to be equals to IS, right? Because all my current is going to flow through here. So then my voltage VL of 0 minus is going to be equals to IS times 0, which is simply equals to 0. All right. And as you can see, since this is a short circuit, right? No or very little current is going to flow through this resistor, right? Because the current is going to take the path of least resistance, okay? So essentially, my current through this resistor is going to be 0, and all my current is going to flow through my inductor. So then the final takeaway from case number 1 says that my IL of 0 minus must equate to my IL of 0 simply because current cannot change instantaneously through an inductor, and this is equals to this IS. And this is what we call the initial condition of this source-free RL circuit. Now we'll dive into case number 2. And for case number 2, what we want to do is we want to analyze the circuit for when t is greater or equal to 0. So essentially what happens is we've disconnected this DC current source from our circuit, and we want to analyze what this inductor is doing. So what I'm going to do is I'm going to redraw the circuit. This is R. There's a current that goes through here, IL. There's a voltage drop, VL, or an induced voltage due to current IL. Call it VL is equals to L DIL over DT. And what happens is when the inductor is disconnected from the DC source, there is an induced voltage VL caused by the current IL. And it allows the inductor to act like a battery source and starts to discharge towards my resistor R. Okay, so what I'm going to do is I'm going to put a plus minus here, and I'm going to do a KVL. All right. So what I can say here is that using KVL, and I made a video on this, so if you need a refresher on that, please feel free to check that out. So using KVL, we can say then that VR plus VL must equate to 0, all right? Because again, this is grounded. So what's VR? VR is this R times IL plus VL is L DI over DT must equate to 0. Let me go ahead and multiply both sides by 1 over L. So then what do we get? We get DI over DT plus R over L times IL must equate to 0. And what I'm going to do is I'm going to rewrite R over L as a variable called A. So I can say then that DI over DT plus A times IL must equate to 0, where A is equals to R over L. And I'm also going to label another parameter called tau, and I'm going to call this 1 over A, and let me call this L over R. And this tau is what's considered to be my time constant. Okay, and it's a very important parameter within the RL source-free circuit. So something important to note is this equation. Okay, so an important thing to note is that since our circuit has no source, we call it a source-free first order differential equation. And the solution to this source-free first order differential equation is what's called the natural response, or the discharging condition of my circuit, right? Of my RL circuit. Okay, so this is very, very important. So we call this the source-free first order differential equation, and the solution, which we'll find out now, is called the natural response. All right, so let's go ahead and find the solution. So the solution to this first order differential equation, what I'm going to do is I'm going to write it out first. Plus AIL of t is equals to 0. So what I can do here is I'm going to move the AIL of t to the other side. So I get DIL of t over dt is equated to minus AIL of t. And then what I'm going to do is I'm going to multiply both sides by dt over IL of t. Essentially, in this term, dt's cancel out, so I'm left with 1 over IL of t times DIL of t is equated to minus A. On this side, IL of t cancels out with this one, so then I'm left with just dt. Okay, so then I can go ahead and take the integral on both sides. And on this end here, it's with respect to DIL of t. And on this end here, it's with respect to dt. So the answer to the first integral is going to be ln absolute value IL of t is equated to minus AT plus a constant c. So then let's go ahead and take the exponential of both terms. So then we're left with the absolute value IL of t is equated to e to the minus AT plus e to the c. But again, this term here is e to the c is equals to just a constant. And this constant can be positive or negative. And as a result of that, we can get rid of the absolute value. Okay? So therefore, we can say then that IL of t is equals to C1 e to the minus AT. All right? So if we wanted to go ahead and solve for C1, from our case 1, we can use our initial condition, which states then that IL of 0 is equals to IS. All right. So when t is equals to 0, our solution is IS. So then we get that IL of 0 is equals to C1 e to the minus A times 0 has to equate to IS. We notice that e to the minus A to the 0 is just 1. So then that means that C1 is equals to IS, or IL of 0. So then now we can write our general solution. And essentially, we can say then that IL of t is equals to IL of 0, or the initial condition, e to the minus AT. And this is what's considered your natural response equation, or how the inductor behaves when you disconnect it from its DC source. So essentially now we know that A is equals to 1 over tau, or again, tau is equals to 1 over A, which is equals to L over R. Again, this is your time constant. So we can go ahead and replace A with tau. So IL of t is equated to IL of 0 e to the minus t over tau. And this is our solution. If you have any questions or comments, please leave them down below and I'll be sure to get back to you. If you like the video, please give it a thumbs up and share the video. And if you like what the YouTube channel is providing, please consider subscribing. It really helps the algorithm. Thank you.